Okay. I had the sudden realization that I left the bag with your notebook in it over on the other side of the room. My bad. I actually asked the college, hopefully they will let me do it. I'm like, let me teach on Fridays from the room. Because then I can just leave all my, I didn't say it this way, but I can leave all my crap. And that would be wonderful. Leave all my garbage. It's not garbage, but it's important. It's important stuff, but, and the notes are posted. They're in that same folder that they've been posted to. Like I said, lecture notes, the lectures are all FUBAR, the recordings. And if you don't know what FUBAR is, ask your military friends. Geez Louise, why is this doing this? Okay. Go away. So, but the notes are all there and they should all be perfect now because I have a really good scanner now and I'm using it well and they actually look really good. I've been checking them. So if there's anything you ever can't read on the notes, don't be afraid to let me know. Let's go ahead and go to Oikos Cam. Move Oikos Cam over to the other computer, which is another nice thing over here. Why I want to start, like, basically, I want to start teaching from the college on Fridays is I love my second computer. Make the chat big over here so I'm looking right at you and let's get started. 2, 16, 20, 21. Okay, so where were we? Where did we leave off? I think I'm gonna have to switch black pens. I need a big thing of good black pens. Where did we leave off? Nobody knows. This is sad. I lectured for hours. I lectured. Hours I lectured. Consonant, we're talking about convergence, consonantal convergence. Excellent. And that was part of a larger discussion about what? What was the bigger discussion? Plate tectonics. Excellent. I have black ink all over my lips now. Hang on a second. There we go. Okay, the comedy of errors always here in GEO 102. Okay, so we've been talking about convergence. We also have talking about plate tectonics. So what two types? We got convergent plate boundaries. That's one group that we've already talked about. What's the other group of plate boundaries that we've already discussed? Divergent, excellent. So what's left? What's left? Transform, excellent. So let's talk about transform plate boundaries. So the side view of, in other words, the cross-section view is not very exciting because transform plate boundaries are basically, they're the equivalent of transform fault. And they're basically a little bit like a fault system. They're basically just a crack in the earth. So if I'm going to draw this, I'm going to draw the lithosphere as I've always done, and the asthenosphere. So we got asthenosphere, and I have lithosphere up here, and we're going to color those in like we've been doing. So we got this brown layer. Oh, and I found the right color brown. What does this brown represent? Does anyone remember from last week? What do I mean? Why do I have that brown there? Crust. Excellent, Megan, Hunter, and Preston. Excellent. We're going to keep this. We're going to keep this what we call in the science of learning and representing things. We're going to call it iconography. We're going to keep this iconography as we go along, where we have the crust brown and the mantle green, because it helps us understand what's going on. So we've got that brown crust, that green mantle. We have asthenosphere spelled incorrectly. And then I'm just going to draw a line like this. And that's our transform. It's basically just a crack in the lithosphere where sliding occurs. Okay, and transform fault boundaries are very common near other types of boundaries. So for example, okay, here we're going to have a map view of the mid-ocean ridge. We're making sure, I gotta scoochie that up a little bit, mid-ocean ridge. Okay, and I am going to draw, I'm going to use my color pens because I have so many and they're so pretty. So if this pink portion is the mid-ocean ridge system, if this is divergent, all along that mid-ocean ridge system, is this purple going to be clear enough? I don't think so. I'm going to do blue. So all along this are transform boundaries. Okay. So transforms often occur. So this is looking down. This is looking if you sliced into the earth. This here is a slice in earth. This over here, on the other hand, is looking down. Now, the easiest way to actually see this is, I think, on an actual map. So hang on a second. Let me grab my globe. I thought I had, I moved it out of the way when I wanted to use the other. So let's take a look at the globe. Okay, so we have a globe right here. I've said the word globe like 12 times. I'm pretty sure you know. And we know that the Mid-Atlantic Ridge System, can you still hear me? We're still in the market for a better camera. Okay, awesome, Megan. It's not the best shot, but here we go. So we have this Atlantic Ocean down the center right here. And running along the center of the Atlantic, we have this mid-ocean ridge system. And basically, it's cross-hatched by a bunch of transform fault boundaries, all up and down and along the mid-ocean ridge. Now, this is particularly important if you're trying to use your book, because your book has this super confusing. You're looking up my nose, hang on. So in your book, this is actually the accompanying lab book for your book. Oops. It does not have it. In your book, the side diagram is a little confusing because the picture of the divergent plate boundary has transforms drawn right into it. Why? Because if you have a divergent plate boundary, you're almost certainly going to have transform. And what's causing that is that as these two are pushing away, the stress is, in other words, the directional force, tension, shear, compression, like pulling away, sliding past each, all of that is really uneven. And that causes basically tears all along that divergent plate boundary. So you end up with these transform plate boundaries all up and along the divergent plate boundary. Another place where we find transform plate boundaries is very often when we find multiple plate boundaries meet. So when we have multiple but they can also occur on their own. And transform plate boundaries, one of the keys here, if we talk about features, putting that in the same spot that we've put all our other features, we really only have earthquakes. We don't have any volcanoes because nothing's getting melted and nothing, basically there's no melting. There's no melting from something deep down coming up like we see at divergent plate boundaries, and we don't see any melting because we have something near the surface sinking down deeper, which is what we see on a convergent plate boundary. Since we don't have a whole bunch of rocks like moving up and down relative to each other, we don't have those dramatic pressure and temperature changes that lead to things like volcanoes. Any questions about any of this before I keep moving? Let's talk about where would we find transform? Where do we find transform by itself? A good example of a transform plate. Keeping up with that. Where do we see it? What's our example locations? Where do we have slipping and sliding like that? Oh, I'm missing my highlights. No, I'm not. There it is. California, excellent. So Preston and Morgan got it. Excellent. So see the San Andreas fault system is part of a transform system. So that's happening because California and the North American plate are basically sliding sideways along along the Pacific. So the Pacific plate and the North American plate are basically going like this relative to each other. The Pacific plate moving this way and the North American plate moving like that. Is it sliding into the ocean? No, it's not sliding into the ocean, and I'm not quite sure. Like sometimes like bad geology, oh, Superman crushed a piece of coal into a diamond, and now everyone thinks that diamonds come from coal. But I have no idea where that bad idea, wishful thinking. I have friends in California. I gotta call my friends in California. Anyways, California has been exciting. There is a really good movie based on the California fault system, basically shows in a fictional way what would happen if every part of the fault goes off at the same time. What's the name of the movie, Laura? See, Morgan doesn't want California to fall into the ocean, I'm assuming. San Andreas with Dwayne. Oh yeah, The Rock is the poop, right? He's just literally the most awesome. So I might have to watch that. Not because I like bad geology movies, although I do. I also just love The Rock. So keeping going. I'm just double checking on our outline so that I am staying really on target and on task. So we're still in wake three major plate boundary types and some subtypes. We talked about island arcs, continental arcs. What plate boundary type makes island arcs? What plate boundary type makes island arcs? Oh, from the ocean convergence. Excellent, excellent, Preston. So convergent plate boundaries, ocean to ocean. What kind of, just reviewing this really quickly because it's on the list of things and I want to make sure that you remember it. What kind of plate boundary system makes continental arcs? What kind makes continental arcs? Those change the volcanoes on the continent. Oceanic continental convergence. Excellent, excellent, Megan. Excellent, Preston. Excellent. So let's actually do the review as a chart. So we're going to make a chart really quickly. Once again, let me know if you can't hear me because I know this microphone is my best microphone right now, but I also know that it's highly directional. So if I move my head out of the way, it can be pretty sucky. So, yeah, let's do ocean continental. We got ocean continental convergence and oceanic continental convergence. Let's go ahead and talk a little bit about what these different features are and make sure that we understand what. So review, we'll call this a review of plate tectonic features. And as a warning, you may need to apply this knowledge to a quiz. So it's good to write it down is what I'm trying to say. So we'll talk about an island arc. Continental arc. Mountain belts. Mid-ocean ridges. Trenches. And earthquakes. Earthquakes? Earthquakes. Okay. A little bit of room because we might need to do more than just a few notes on each one of these. It might be more than a yes or no, although a lot of them will be just yes or no. So divergent, convergent, and transform. Do this. So we have the column set up nice. Nice column. Okay. So island arcs. Where do we find island arcs? Divergent, convergent, or transform? We already said it, and it was correct. Is that the only place we find it? Ah, come on, man. Convergent, excellent. Thank you, Preston. So convergent is the only one we see this. We definitely see this. And we see this, as you point out earlier, as an ocean-ocean convergence is going to give us an island arc. We don't see it with divergent, and we don't see it with transform. What about continental arc? Continental arc. Ocean continental convergence. Excellent. Excellent, Megan, too. Ocean continental convergence. Do we see it with divergent or transform? See a continental arc with divergent or transform? No, excellent. Yes. Ocean, continental, convergence. Now, mountain belts. Where do we see big mountain belts? Where do we see big mountain belts? Convergent, continental, continental. Excellent. Preston, is that the only one? So with convergent, you see it all types. You actually see all types makes mountain belts. However, the biggest, like the Alps, the Himalayas, are, as you point out, continental to continental. We didn't talk about it much, but we also see mountain belts at divergent plate boundaries. We see small, low fault belt mountains. And we see these, like, for example, the Sierra Nevadas and the African Rift Valley. So we'll see mountains in divergent plate boundaries if they're young divergent plate boundaries that are occurring on a continent. We'll see, and they're not the big bada boom convergent plate boundary, like big mountains like the Himalayas that we see at convergent plate boundaries. Transform, nope. There can be sometimes, but not usually, no. or at least doesn't have to be. Okay. So, I mean, you can see a transform in a mountain belt, but that's not what's causing the mountain belt. Mid-ocean ridges, which plate boundary type? Remember, I am very likely to ask a quiz question based on this. Divergent, excellent, Megan. So yes, we see mid-ocean ridges. What about convergent and transform? We're going to say no on both convergent and transform, but once again, it doesn't, not the cause. In other words, you might find transform. Yeah, you can find transform near a mid-ocean ridge, but not always. Not the cause, not always. Whereas you're almost always going to see an island arc with an oceanic convergence. You're almost always, and the constant oceanic convergence causes the island arc. The oceanic continental convergence is causing the continental arc, but the transform plate boundary is in no way causing the formation of the mid-ocean ridges. So we don't usually see transform plate boundaries at mid-ocean ridges. It's a little bit like that coal question. Some people pointed out you can find minerals like pyrite in coal sometimes, but it's not part of the definition of what makes coal coal. You can find coal that has no minerals in it and it would still be coal. So you can find mid-ocean ridges that have no transform plate boundaries. Okay, and they would still be mid-ocean ridges, and those mid-ocean ridges are caused by the divergent plate boundaries. Because Earth is hella messy. Earth is a messy lady that doesn't follow all the rules all the time. We're not like physics over in earth sciences, where physics is like, this is the way it is all the time. All the time, this is the way it is. No, there's lots of yes, but kindas, because we're talking about dirt and rocks at the end of the day. So, and I love dirt and rocks. I love it. Okay, so trenches, divergent, convergent, transform. Who's causing the trench? Good thought. It's actually just convergent. Specifically the ocean, and ocean continents. Not the continent. There's too much squishing going on there for a trench to form. But in a convergent, in an oceanic or an oceanic continental, you're going to find a convergent, a trench. But you're not in a divergent or a transform. Okay. So I just have a question. Why does everyone seem to think that trenches are with divergent plate boundaries? Because I have that problem in every class, and I'm wondering if I explained it pooey or I said something confusing at some point, because you're not the first class. I've been doing this for like a long time. We'll put it that way. Dr. Evie's been doing this a long time. Any particular reason why you thought it was divergent? Because that's always happens. People put that on the test as like a wrong answer all the time, because I think of divergent as pulling apart and stuff falling down. Thank you, Preston. That makes a lot of logical sense. Yeah, so like when you think of it pulling apart, of course you visualize a big old hole forming, but that's not not how it rolls, because something is moving up to fill that space. So it's not that like if they were pulling apart, it's just like a big hole and now there's just this big gap there. There's lots of stuff flowing in to fill it. So earthquakes, where do we find earthquakes? All of them. That one's divergent. All of them transform. All of them. So Preston has the best answer. Yes. 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 And just as a heads up, we're about to move into earthquakes. So this is a wonderful segue into earthquakes. But this is also deep ones. So the biggest, worst, deepest earthquakes come from convergent plate boundaries. So, I was trying to think of what I wanted to say and show you. I'm going to show you a map in your book. So let's take a look at a map in your book. I don't know what map, what page it's in your book, but it's and in the plate tectonics chapter, but it's a different page than this physical copy. It's in the earthquake chapter. They just keep moving around where the earthquake chapter is. I think to get us all to buy a new book. But if we look here, this is a map of earthquakes, okay? So these are all the earthquakes, not all the earthquakes, but distribution of nearly 15,000 earthquakes with magnitude equal to or greater than 5 for a 10-year period. So that's all the earthquake dots all over the place. These earthquake dots are basically outlining the plates. So there's such a connection between plate boundaries and earthquakes that the lines of earthquakes are basically the lines of plates. So like this right here is a plate boundary. This right here is a plate boundary. This is a plate boundary. This is a plate boundary. All of this is a big mother of a plate boundary. This is crazy amount of plate boundary in the Alpine Himalayan belt as like several things slam into Eurasia. Okay, so this right here, so maps, basically maps of earthquakes. Outline the plate boundaries. Now, can you have an earthquake where there is no plate boundary? Yes. That's actually not totally uncommon. So for example, the Adirondacks are not on a plate boundary, and we occasionally will experience earthquakes. It's for similar reasons, but it's not, and like I said, hopefully we'll have time to talk a lot more about how the Adirondacks formed towards the end of the semester, but basically it's a plume of mantle material that's rising up underneath it, and that causes similar stresses to a plate boundary, even though it's not really a plate boundary. So this is a fantastic segue into our next topic, which is, let me make sure that's not a student. That is a student. Hang on a second. Very sorry. This is a very uncomfortable way to teach, but so be it. Oh, okay. Yeah, no, it's not this class. That was for GEO 110 next. Okay. So, and please forgive me. I just want to say that right off the bat. It's easier looking into my little eyes Please forgive me if I mix you up and get you mixed into a different class. I do recognize your name. I'm not always, like, it's hard because, I mean, I teach really similar stuff too. So I remember talking to Preston about plate boundaries, but right now I'm talking to like 3 different classes about plate boundaries. So I may accidentally think, for example, Preston is in GEO 110, even though he's correctly in Tuesday, Thursday, GEO 102. So if I ever get that mixed up, please forgive me. And correct me. Like, I just met a student for the first time in person, and she was like, yeah, you've been saying my name wrong this whole time. She did it much nicer than that. She was super nice. She was super nice about it. But I was like, aw, I'm glad I know it. So yeah, let me know that stuff. Okay, the awkwardness of online learning, man. Okay, let's segue into earthquakes. Segue into earthquakes. Okay. So what is, nope, sorry, you were supposed to be perfect. Thank you, Preston. Thank you for reminding me that you all are human and you recognize that I am human. So I appreciate that. But I really try and I want to know all of your names. I really wish that I could see all of your faces. Anyways, so let's talk about earthquakes. What is an earthquake? What is an earthquake? Movement of the plates. I'll start with that. So an earthquake is plate movement. It's not always plate movement. It can be caused by plate movement. So earthquakes, what's the basic idea? So movement of the plates is definitely the major cause of earthquakes. Like way over 90% of earthquakes have something to do with moving plates. But what is an earthquake really? What's the ground doing? Shaking, excellent. So earthquakes are really vibrations that cause movement in the earth. So earthquakes can technically are not all caused by what we classically think of, like things like plate movement and that kind of stuff. It can also be cave collapse. It can also be nuclear detonations. So so like if you, for example, are North Korea and you're like, I'm gonna be all sneaky and test a nuclear weapon underground. The #1 signature we get from that is an earthquake, but that earthquake is going to look and feel a little bit different than other naturally formed earthquakes. So earthquakes are represented in what kind of a, does anybody recognize these 2 words? I'll put it this way, a seismograph and a seismogram. What are those things? What's a seismograph and what's a seismogram? Yes, I forgot what they mean though. Thanks for being honest, Megan. What do they have to do with? Yes, Preston, excellent. So seismograph measures and records earthquake waves. And the seismogram is the recording of the earthquake wave. Excellent. They measure the movement in the ground. Yes. So, yeah, so they measure the movement in the ground, and they measure basically the moving and the shaking of the earthquake waves. So to really understand earthquakes, because earthquakes are a type of wave, we need to understand a little bit about waves first. So let's talk a little bit about waves. So a wave is an oscillating or repeating motion which moves energy, but not matter. So we're going to look at an example, and waves are going to come up quite a few times in this class, particularly when getting to astronomy, because we're going to be working with stuff like light, and light is a wave. So waves are an oscillating motion which moves energy but not matter. So if we take a look at an example here, like this, okay? So this is our example wave. If we measure from crest to crest, this is the wavelength. If we measure from the middle here, actually, let's use a different color. So from here to here, or from here to here, this we call our amplitude. And then we have another way to measure wavelength. We could do from trow to trow. This is also wavelength, same length. Okay, so we now have an idea of what a wave, and I say example here because not all waves look like this. Okay, this is what, like, for example, water waves look like. And the advantage of water waves is that they behave like waves do, so we can use them for our descriptions. But they're also really, 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 really familiar to us because most of us have seen waves on the water before. So let's go ahead and talk a little bit more about seismic waves. So seismic waves are waves from an earthquake. So let's get a little bit seismic waves are waves that are caused by an earthquake. So now that we have some of these definitions to work with, we can actually get a little bit, we have a picture of a wave. We have an idea of what a seismic wave is, what a seismograph and a seismogram is, and what earthquakes come from. Now we can get into a little bit more about what earthquakes are and where they happen. So earthquakes start, important idea, earthquakes start in the lithosphere. And they're caused by the rigidity. So it's caused by rubbing, in other words, friction on the rigid lithosphere. So earthquakes are always going to start in the lithosphere, and they're always going to start where there's some kind of rubbing in the, yes, I can definitely move the paper up. Sorry, I didn't see that right away, Preston. They always start in the lithosphere, and they're always caused by this kind of rubbing. And this is why we see them so frequently at plate boundaries. At plate boundaries, we have a lot of lithosphere rubbing up against each other. So we've got this rubbing going on between the surfaces of the different pieces along the plate boundaries. So because we see a lot of that rubbing, that's where we're going to find our earthquakes. So does everybody have this? And can I flip the page? That handwriting is terrifying. That is terrifying handwriting. Awesome. Give me like 45 secs. You mean 45 or 425 secs? I'm going to assume that it's 425 seconds. So we're going to take a look at it. Next thing up that we're going to talk about is the epicenter and the focus. So most earthquakes don't originate, we're talking about rubbing going on. So most earthquakes don't happen necessarily at the surface. They happen actually deep inside the earth. So we're used to hearing about the word epicenter, but that's different from the focus. So I am flipping now. I am sincerely sorry, Anthony, but we gotta keep trucking. Okay. So so earthquakes happen at faults. Faults are cracks in the Earth's surface in the Earth's bedrock that have experienced motion of some sort or another, okay? So there's another word for cracks that don't have motion. Those are called joints, okay? We're not gonna worry about too much. We're just worried about what happens when these things rub up against each other and we have motion. So I'm gonna draw a cross section. Okay, and this is not to scale. So I'm gonna draw the surface. I'm gonna put a little house, what a pretty little house right there. Okay, and this whole big chunk right here, this is lithosphere. We've got the crust up top. And the mantle extending down to the bottom. Now the fault may extend all the way through the lithosphere. Got an odd question. Could the underground detonation of nuclear weapons get create new fault lines. If it was big enough, if that was a big bada boom, I don't think North Korea has that capability, but I mean, I know that the USSR and Russia and the United States has set off some pretty intense stuff. I'll have to Google it. So that's definitely a Googleable one. So, and here we have our fault. Ooh. Okay. And along this fault, we have our point where it just got, the stress got too much and there was basically like friction and sudden motion, sudden vibrations occurred. So here we have this portion right here. This is called the focus. Okay. So the focus is that position inside the earth where the earthquake originated. Then up here, we have another position, and this is called the epicenter. So remember, once again, this is basically a slice into the earth, right? So we're looking at a slice into the earth. This is a little house right here. So we have an idea that this is the ground. Little people. There's another person. All right, little people, little house, that sort of thing standing on the surface. Up on the surface above the focus is the epicenter. And so the epicenter is the location on Earth's surface above the focus. So in the news and stuff, they're obsessed with the epicenter because that's going to tell you where the town is, where it was located, and that kind of stuff. Okay, like where the earthquake was at Northridge in California. Okay, so everywhere on the news talks about epicenter, but that's not really where the earthquake is happening. Where the earthquake is really happening is deep inside the earth at that focus. So does anyone have any questions about any of this before I keep moving? No, excellent, excellent, Hunter, excellent, Megan, excellent. So there are 4 major types of seismic waves. Okay, so those are P, let's actually turn this into a chart. This is definitely chart time. Chart is the best way to organize this data. So, we'll talk about body and surface first. And then we'll talk about the 4 major types, P, S, L, and R. Okay, so body versus surface waves is exactly what it sounds like. Body versus surface. Body is a seismic wave that travels through Earth's interior And a surface wave is a seismic wave that passes over the surface. So, oh, can I please move it up? Please, says Megan. I'm so sorry. Thank you, Megan, Hunter. I'm very sorry. Sadly, I would love it if chat could have a noise like it does. I guess it doesn't. I guess that's not a possibility. So it's another advantage of Collaborate. It has like a doink noise when somebody posts something. So I'm like, oh. So my apologies. If I don't, I'm gonna blow this up. So it's my number one thing. So P, S, L, and R are their four major wave types. So the first thing we're going to discuss is their motion. And for this, I'm going to go ahead, for the P and the S waves, it's useful for me to grab a slinky, which is one of the reasons I'm glad to be working in my lab. I can actually show you a slinky. So, because it's not like I wouldn't have a slinky at home if I remembered. The thing is, would I remember to bring home my slinky? So, let's go ahead. So we have a, slinkies are great for demonstrating seismic waves, okay? So we're used to waves that do this, right? They go up and down like this. And if I was even better and I had a student who was able to like hold on to the end of this, I could shake one end and it would, like a single wave would just travel up and down this slinky. So that's what's called a shear wave, and it's the wave that we're used to seeing because that's the wave that that are like water waves and that kind of thing. Now P waves are a little bit different in that they're compression waves, the same kind of classification of waves that sound is actually. Sound is a pressure wave. So I'm going to bring you down here and then show you. So this, when we say a pressure wave or compression wave, this is what we mean. See that squeezing, how it's traveling along the slinky? So one type of wave is this kind of wave. We're used to like up and down, side to side motion like that. A P wave or a pressure wave is more like that squeezing. And we can even see a little reflection there, right? So I push that and it bounces back. Okay, that's my slinky. Could you hear any of that while the camera was on this? Excellent, excellent. Thank you, Anthony and Megan. So, interesting question. Where did the pen go? There it is. Okay, so motion P waves are pressure or compression waves. So that squeezing that we saw. Okay. Oh, so you can see the writing on the wall, right? So pressure and compression. S waves are shear waves. Now, L actually stands for love and R for Rayleigh, which aren't like, you're like, oh, it's a love wave. It's not nearly as romantic as it sounds unless you're really into mathematicians. So, because that's what love is named after. Love waves are named after. Basically, L waves move left to right, and R waves move up, down. So that's their general motion or description of their motion. These waves can also be divided up by their speeds. So P waves are very fast. S waves are kind of slow. L and R waves are very slow. And then finally, they can be broken up into body or surface waves. So P and S waves are body waves, and L and R waves are surface waves. And then a lot of people are like, but what kind of waves make your house fall down? It depends on how close you are to the epicenter, okay? So for most damage is actually L and R waves are incredibly damaging. However, in certain circumstances, the P waves can also be extremely damaging. So let's go back to our friend, the plot of the PS, L, and R waves. So I am going to draw. Okay, so I have this sketch. I'm going to go wooja, 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 wooja. And this is hugely exaggerated. Wooja, 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 wooja. Okay, like that. As some very artistic looking seismic waves. So by artistic, I mean Dr. Eby cannot draw. So, so is this a seismogram or a seismograph? Or just a crappy drawing by Dr. Eby? No, what is this supposed to be, a seismogram or a seismograph? Excellent, Anthony. So this is a seismogram. Now let me tell you, let me be real with you for a moment. Looks like an upside down tornado. That is because I suck at drawing, Megan. But I will give you, I may suck at drawing, but I'm excellent at studying. That's how you get a PhD, is you're not necessarily smart, but good Lord, you know how to study. So a seismogram, to keep them straight, that it's a mnemonic device. The M looks a little bit like the Wiggles to me. And I came up with that in like undergraduate, because like I would get seismogram and seismograph mixed up. So if you're ever like, I want to keep these two straight, which most semesters is important. But in this semester, you can always Google it if you don't know. So I guess it's slightly less relevant, but that M looks like the Wiggles on the seismograph and seismogram, and that's how I connect. Oh, the M is the Wiggle. Okay. So there's a seismogram recorded by a seismograph. Okay. And this is the start. Let's call this time. Well, actually, like even better yet, let's actually use like real time so this makes sense. So if this is like 1 o'clock p.m. and then over here, it would be later in time as like probably about 1:15 p.m. Okay. So you can see that this is the start of time and this is the end of time. In your book, they'll always end up labeling this 0. And I think that screws up students a lot, because they look at that and they're like, oh, the start of time is time 0. No, it's just that we encountered this seismic wave at about 2 minutes past 1 p.m. Okay. And then we recorded that shaking for a period of time, and then that shaking stopped. So in this diagram, we can divide this up into our different waves, okay? So this first wave right here, this is our P wave. Our second wave right here, because it's slower and it comes right after the P wave, is our S wave. And our last wave over here, this is our surface waves, which is our L and R waves. Make sense? A little bit? Yes, good, 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 good. I'm gonna assume good. I'm gonna keep going as though it's good. Okay. So, so P and S waves are particularly valuable for geologists because they travel through the Earth. P and S waves are very valuable for geologists to determine the location of the earthquake and the time of the earthquake and many earthquakes and earthquake data can be used to piece together what is going on inside of Earth. Can I push the page down or there we go. So this is an important point. You may want to write this down. I'm going to surround it in orange like that. No worries, no worries. So earthquakes are basically earthquake data is used to piece together the inside of Earth and also piece together where the earthquake happened and the time that the earthquake happened. Now, I don't think we have enough time right now at this second for me to go through the whole explanation of how you use this graph to determine the location of the earthquake, how you use the seismogram to determine the location of the earthquake. So I know we're a little ahead of time, but I might say, let's call it quits here and get back together next time on Thursday. Now, quick reminder, stuff is due Wednesday, the 17th. So remember, and of those two, the quiz or the Pearson work, both are important. Both can get you power-up points. Get those both in and you will get your power-up points. But if you have to judge one, you can turn in an infinite number of the Pearson stuff late. You can only turn in 2 quizzes late. So if you're saying to yourself, oh my gosh, I don't know which one to do, focus on the quiz. And don't be afraid to email me about the quiz. A couple of people, like very few people have emailed me. And I saw on the last quiz that there was, most people got it, but there were a good number of people that were confused or looking in the wrong spot for information. And actually, like, almost most people got Abdul's and Jones' basic ideas of like, is it a rock, is it a mineral? It's a rock, not a mineral. But most people ignored the second half of Jones' statement about like, it's a rock that contains minerals. So if you're confused about your points, I posted the rubric in the student feedback section. Let me know if you're having trouble viewing it, because for me, that might be the easiest way for me to make sure that I can get through all your stuff quickly. Like, and so that, and the benefit to you then is that you get feedback really fast. Which is why I'm doing the small quiz thing, is because, and this week's quiz is a little long. They're probably going to usually be 1 or 2 questions. Because I don't want to overwhelm you with work, but this week's quiz is 3 questions. So Any questions about any of that kind of stuff before we break up? Like quizzes, how they work, where your points came from, all that kind of stuff. I'm trying to really keep up with. Nope, all good? Awesome. Awesome. Cool, cool. So yeah, and the folks that I know all the people who got PowerPoints got an email, like, and I do notice that you're showing up and paying attention. Yeah, thank you for showing up and paying attention. And I hope you have a great rest of your day. I've got diarrhea of the mouth right now, apparently, and you all have a great afternoon.